Hi everybody. This video contains new concepts, the normal space and the tangent space to a surface, which will be extremely important when we think about flux and electricity and magnetism in the future. Now, I'm going to first solve the problem and then I'll explain further at the end of the video. So first I'll just give you the solution, how I would write my solution. Okay. Consider the surface given by the image of this map. So we have 1, 2, 3 component functions. So the surface will live in three-dimensional space. And here it is. It's this blue surface. It's called a helicoid. And you can click on our homepage and get this GeoGebra app from the Canvas homepage. At each point, there's a normal space and a tangent space. Describe both at the point P equals f of 2 comma pi over 4. Okay, so first I'm just going to name this point Q to be 2 pi over 4. And so now we could say that P is f of Q. Right, so Q is an input space, it's in R2, and P is a point here, actually right, let me get a different color, right there, this point on the surface. And you can see actually here's the tangent space. And well, actually here is the tangent space, and here is the shifted tangent space to start at the point P, which is f of Q. The normal space is then sort of sticking out at 90 degrees, and it's the entire line spanned through this normal vector, which means it's all the vectors that are orthogonal to the tangent space. Okay, so let me write this out. So the tangent space is, well, the tangent space at P equals f of Q is the image of what map? It's the image of a map. The image of the derivative at Q, or we'd say derivative of f at Q. Okay, so it's the image of that linear map, which is why it's a plane. It's a linear flat plane. Okay, then I'll say the normal space at P equals f of Q is the space of all vectors orthogonal to the tangent space. Okay, so this is the tangent space to the surface at the point P. This is the normal space at P to the surface we're calling S. Okay, so what do we need to do? We need to first take the derivative, because the tangent space is the image of the derivative map. Okay, so let's take the derivative. The Jacobian has columns from, coming from the derivative of the two input variables. In this case, our map is from R2 to R3. Well, so we take d by dx1 and d by dx2, period. And then I'll write Jacobian equals. So now I have to take the derivative with respect to x1 on all three of these, and I get that's my first column of the Jacobian matrix. Now I take the derivative with respect to x2 of each of these. Okay, and those are my two columns of the Jacobian. And now I can create the derivative. So I'll say the derivative is a linear map, well, the derivative where? The derivative, well, of f at the point q equals what? 2 pi over 4, that was q, is the linear map. So now I have to write down a map, okay? The input space is R2, so I need V1 and V2, and I'll send those two real numbers to a new point, which is V1 times the first column of the Jacobian plugged in. And so take your time and plug this in. Remembering your unit circle, you'll get this vector. At the point Q, we plug in and get a vector. And then I just take a linear combination of these two vectors where I plug in here. And this time I will get, so here the 2 and some 2's will cancel, so you have to do this computation yourself. And so there we go. So let's call this, well, let's give it a name. This is the map DF at Q. So then I would say TPS equals the image of DF at Q. And that's it. And visually, that image is this entire plane. It extends out actually, forever. Inside of three-dimensional space, it is a two-dimensional flat plane. Okay. Now I need the normal space. Remember, the normal space are all the vectors orthogonal to the tangent space. And we know that our tangent space is linear combinations of these two vectors. And so what do we do if we have two vectors spanning a plane? To get the normal vector, we just take their cross product. The normal space at S is equal to the image of the map. Well, now I have one real number, and I'm going to send it to R3, and it's going to give me this entire line through that normal vector, and it'll say V1 times the cross product of these two vectors. 2, 0, comma, and then a second vector to take the cross product. And the cross product of these two vectors gives me a new vector. Here it is in the picture. And I just take all multiples of that vector, which fill out a line. That is the image of this map, sending R to R3, giving a line inside of R3. And that is the end. So I calculated the Jacobian matrix, which allowed me to define a map. It's a linear map. And its image is the tangent space. The normal space, then, is the image of another map giving a line of all possible vectors that are at 90 degrees. Okay, now I will explain a little bit more this picture. So this is it. This is the end of your answer. But now I'm going to explain a little bit more. So in this picture, we see that the tangent space passes through the origin, the point 0, 0, 0. So the tangent space contains the origin. But you might rather think that the tangent space should be shifted over here to go through the point. This is the point P equals F of Q. On our surface, it's a point on our surface, and so you'd think it should go through that point. And so if you want to do that, you just remember our formula for linear approximation. F of x plus v equals f of x plus the derivative of f at x applied to v. And now this is only actually approximately equal. And so you see that this plane here, it leaves the surface. Like over here, this point on the plane is off the surface. But it's pretty close. Especially near to this point, it's very, very close to the surface. Okay, so this is the shift. And then this is the linear part, giving TPS, the tangent space to our surface S at the point P. And so if we wanted to parameterize this plane, all we have to do is say it's, this, so I'd say the shifted tangent plane, TPS, is the image of the map. So it's a set of all possible outputs when I plug two real numbers into this map, where I go to P equals f of 2 pi over 4 plus v1 times this map, times the derivative, or just basically this piece is going to be the derivative. What was it? I think it was minus root 2, 1. Was that right? Yeah. So you see that here is the derivative, giving the tangent space, and here is the shift. Now, how could I do, this looks like a three-dimensional vector. I add to another three-dimensional vector. What's this? Well, it's got to be a three-dimensional vector, of course. So if I plug in 2 pi over 4 to the map, what do I get? I get 3 numbers. I have to plug in, and I say I get root 2. And here I get root 2. Plug in and check this. There's some canceling I'm doing in my head because I've done this problem already, but you should check this. And then this last point is pi over 4. And so this point here I can write as a three-dimensional vector. So I could, that was a little too much. I could write it as, what was it? Root 2 pi over 4. Root 2 pi over 4. And so that's the shift. And we've seen this all the time when we use GeoGebra to plot vectors and then move their tails so that the vector starts at a different point. What we do is we just add that shifting factor. Well, it's not a factor, it's a term, a shifting term, because we add it, not multiply. Okay. Excellent. So I think you should, review what the image of a map is. That's from even problem 1, 2, and 3 maybe. And now we have the image of a linear map. The image of a linear map is a plane. It's that plane and it goes through the origin. Now let's do that for a second. If I plug in 0, 0 to this linear map, the derivative, what do I get? I get 0 times a vector plus 0 times a vector. And so when you multiply 0 times a vector, it just gives you the 0 vector, you add them up and you get exactly the point, 0, 0, 0. And that's why the tangent plane contains the origin when we don't shift it, right? So now if we plugged in 0, 0, 0 to this shifted map, what we would get is root 2, that was supposed to be root 2 pi over 4 plus 0, 0, 0 when we plug in 0 there and a 0 there.